This video is on taking square roots with Napier's bones. Napier's bones is an early calculating device, and what it consists of are strips. It's basically a multiplication table that you might see in an elementary classroom, but it's cut into individual strips. And this set that I have comes with two sets for each digit. It also comes with a square root bone or rod, and also a cube root bone or rod. So in this video, we're going to focus on taking square roots. I do have two sets of these so that I can have more than two copies of 8 digits. So this then works as a frame in which I can do my work. You don't actually have to purchase one of these. You can make your own. So I've gone to the hobby store and I've also made my own bones or rods. I'll be going back and forth between using the word bones, rods, and strips. I mean the same thing by each one of those. And then I also made my own square root rod and my own cube root rod. So you can do that, but these are also available online if you want to go that route. So the first example that we're going to do is to take the square root of 1024. And in order to do that, you write the number that you want to take the square root of, and you break it into doublets. When we're working with square roots, we want doublets. With cube roots, we want triplets. So the first thing that I'm going to do is to put my square root bone in here, and I want to get the closest square to 10 without going over. So you'll notice this rod is made up of a lot of different strips, but all I'm concerned about is the square root portion of it. So the closest square to 10 without going over is 3 squared, which is 9. So the first part of my answer is a 3. Square that, you get 9. I'm going to subtract that off and then bring down the other doublet. What we do is we take the 3 and we double it. We multiply it by 2. And you can actually see that result on this rod. There's a little row of doubles here. So I need a rod for 6. And what I'm going to do with that is put it in front of my square root strip or rod. Then I'm only focused on that strip and also the perfect squares that are on the square root rod. I'm trying to find the number that's closest to 124 without going over. And I should have maybe talked a little bit first about how to multiply on this. But basically, you've got the only thing we're multiplying with is the 6 strip. The first square there represents 1 times 6 or 6. 2 times 6 we get 12. So this is the tens place and the ones place. 5 times 6 is 30. 3 with 0. But we are augmenting this with the square root strip. So I'm looking across these rows for the closest thing I can find to 124. So this is my ones place. This diagonal here is my tens place, and this is my hundreds place, and I literally see the 124 sitting right here. So the next part of my answer is 2, because that's the row in which I found the number that I needed. That's 124. And so our answer to the square root of 1024 is 32. So I'm going to do a total of 4 examples. I may explain it one way with one example, another way with another example. So hopefully, as we look at a number of these, it'll be helpful as you try to do this. So the next example I have is 46,656. I'm going to reset by just having my square root bone in there. We're going to rewrite this number 46656. We're going to split it into doublets. This time you'll notice I have a pair here, and the 4 is all by itself, but that's perfectly fine. So we start again on the left-hand side. I want to find a perfect square as close to 4 as possible without going over. Well, there's one sitting right here. 2 squared is 4. So the first part of my answer is 2. I square it, which is 4. I subtract, and it basically cancels out or gives me a 0, and I bring down. In order to determine what rod I need to expand with, I take the 2 and I double it. So I know it looks like it's the same 4 in both places, but this is 2 squared and this is 2 doubled. You get the same result. So I take a 4 strip and I put it in front of my square root rod. And I'm only going to focus on these first 2 columns that I see. And I need to find the closest thing to a 66 without going over. Well, in the first row, I see a 41. In the second row, I see an 84. That's already over 66. By the way, if you keep going, you are going to need to do some carrying. So down here, if I have the 9 row, this is going to be 441. This is in the ones place. You have a 6 plus 8 in the tens place along that diagonal. So then that gives us a 14. You put a 4 down here, carry the 1, and add it to the 3 for 4, 4, 1. So that's how that works. So the closest thing to a 66 I can find is in the first row, it's a 41. The 84 is too high. So the next part of our answer is a 1, because that's the row I'm working with. I write the 41, and I subtract, giving me 25. And then I bring down the rest of my original number. To find out what rod to add to this process, I double the 1, giving me 2. Now where this is going to go is right in front of the square root bone. So it's going to go in between my first bone and my square root bone. So here we go. Again, I don't really need to be for this, kind of just for reference. It's the digits in order. And then these are your doubles. So those are just kind of references. This is really what we're working with right here. So I want to find the closest number in a row to 2,556. Since this is a perfect square, that number will be sitting there if I've done everything right. So what I do to kind of speed things up is I look for the 6 in the ones place. I see a 6 here. Well, and actually look, I've got a 6. 2 plus 3 is 5, 4 plus 1 is 5, and I've got a 2. 2, 5, 5, 6 in the 6th row. So the next digit of my answer is a 6. That row gives me 2,556, and I have finished my work. So the square root of 46,656 is 216. The next example, we're going to go with an even bigger number, and that is 233,289. So we will just reset, put away these rods here, and we begin by writing our radicand, the number we want to take the square root of, and splitting this up into doublets. Those are not decimal points, you're just splitting the number. The first thing we look at is the 23 in the front. We look along this first column to find the closest number without going over. I mean, this you could do in your head, right? Just what square is closest to 23 without going over? Well, it's the one below 25. So we've got a 16, which means the first part of our answer is 4, because 4 squared is 16. That's the row we were working in. We're going to subtract and bring down, but then to figure out what I need to do for my next step, I double this 4. And I can also see that sitting right here. I didn't need to write that down. It's right on the rod for me, very conveniently. So I'm going to take an 8 strip, place it here, and I'm trying to find the number closest to my most recent result, which is 732. So as I look along here, this is 81, 164, 249. I need to move up quite a bit further. I want a 732. I see a 700 here, but that's too high because there's going to be a carry, putting it in the 800s. So it looks like this is the correct row here, the 8. We have a 4 in the ones place. 6 plus 4 is 10. So we have a 0, but then we carry the 1, and 6 plus 1 is 7. So that's the closest result I could get without going over. That came from the 8th row. And look, if you double an 8, you get a 16. I could just refer right here. Very handy. Now, the reason I wanted to include this example is because the next rod that I need to use is a 16 rod. Well, I don't have a 16 rod. All of my rods just have a single digit up at the top. So imagine, though, grabbing the 1 and the 6. I don't want to put 2 rods in here because that would mess up place value. There's place value that's naturally being taken care of. So what we're going to do is put the 6 of the 16 right here next to the square root rod right in front of it, and 1 and 8 are going to become a 9. Basically, we carry, right? 16 plus 80 is 96, and that's what just happened. So I hadn't done my subtraction over here. Let's go ahead and do that. 732 minus 704 is 28. Bring down the 89. Now I'm at the back of my number, and I set this up to be a perfect square. So if I've done everything right so far, that number itself should be sitting right on one of my rods. And again, kind of my shortcut is just to go down the back and look for the 9s in the ones place. I see one here and I see one here. Which one is 2,889? Well, it's going to be this one here. I get a 2, 7 plus 1 is 8, 8 plus 0 is 8, and I have a 9, 2, 8, 8, 9. So that's in the 3rd row. So our answer is 483. And I just felt like I needed to finish off my subtraction there. So that's our result. So one question that might come up is, what if you start with something that's not a perfect square? Can you actually get into decimal places? And yes, you can. You just continue using the same process. I'm going to use the square root of 2, which a lot of people are familiar with. If you've worked, if not, grab your calculator. But if you've done any trigonometry, you know that's 1.414, right, approximately. So in order to do this, I'm going to reset. And I have my number 2. And to begin with, I want to look along here to find the perfect square closest to 2 without going over. Well, that's a 1. So that's going to be the first digit of my answer. And it seems like I'm done, right? Because I'm out of digits. 1 squared is 1. I do the subtraction. I've got a 1. Well, just like when you're doing division with decimals, you can actually add 2 zeros to the back. We're going to bring those down. 1 doubled is 2. We just use the same process. So I will put a 2 in front of the square root bone. And now I need to find the number along here, which is closest to 100 without going over. So I see a 44, a 69, a 96, and then a 125. So we need to go with 96. That is in the 4 row. So that's the next part of our answer. Subtract, and as you want to keep going, finding decimal values, you just put in 2 more zeros and drop those down. The rod or bone that we use is going to be the double of the last digit that we found. So that's an 8. We're going to slide that right in here. And we're going to look for the row that gives us a number closest to 400. So let's see. It's a 4 in the ones place, 6 in the tens place. This is a 5. This is already 564. So my next digit is going to be a 1. And that gives me 281 as a result in that row. So the next part of our answer is a 1. We get a 281. We continue doing our subtraction. I didn't leave myself much room, but you could throw 2 more zeros on the back of that. Do your subtraction. 400 minus 281 is going to be 119. Bring down the 2 zeros. And if we double the 2, it tells us what rod to use. So we bring that in. Notice I've used up both of my 2's from this set now. That's why I wanted to have an additional set. So if I had more than 2 of the same digit, I could continue my work. So at this next stage, I'm looking for how I'm going to get an 11,900. So as I go along, let's see, this is going to be 2,821. That's way too small. I'm seeing an 8 plus 3, which is an 11 here. So it's going to carry into the thousands place. So let's see, we've got a 6 in the ones place, a 9 in the tens place, a 2 in the hundreds place, and then this 8 plus 3 gives us an 11. And so that came from the 4 column. And I started adding zeros to this just after my first operation. We worked with the 2. We found that our first digit was a 1, but then we needed to start adding zeros to get into the decimal places. So our result for the square root of 2 is 1.414, which does agree to the first 3 decimal places, and you could just keep going. You just continue this process. So the question might be, well, why does this work? Why is it that you are multiplying by numbers out here, and in fact you continue to include the ones you've already used, but at the back it's like you're just adding the squares onto that? And so I played with that a little bit. This is actually a recording for me to remind myself of what I figured out as I read through Napier's work and figured out how to do this. So to consider a 2-digit number and square it, I thought about breaking up the digits of that number and making an addition problem. So technically we could put place value in here and say that this is 10a plus b, but for now let's just look at the structure that we have. So I can see where the doubling is coming from, but it makes a little more sense if I break this up differently. So the first part of the process, remember, is always just finding a square. Well, that's a times a, and a is the first part of our answer. Then we're looking for b, which is the second digit of our answer, right? This is from the 2-digit number AB. And then we have this double of a. Oh, we had to double our first result. And you'll notice the plus b back here, if you distribute the b through, that's going to give you a b squared. Technically the a is a 10a, and that takes care of your place value. And I did that for a 3-digit number as well. So if you take a trinomial and you square it, that is the structure of it. But if you rearrange things a little bit, you see that you can take the a squared and write it as a times a. A is the first digit of our answer. B is the next digit, C is the next digit, and as you keep going, you have a piece where you've got whatever result you got previously doubled, plus your new answer. So that's going to be b times b, which is b squared, and that's why we have these squares at the back every time. Moving on to the third result of our answer, we get c. C times c is c squared, which is going to be on the back, and we get 2 times a plus b, which is why we keep both the a rod and the b rod in there. And I took it just one more step. So if we've got a 4-digit number and we're going to square it, that would be basically the equivalent of doing this. We get all of these terms. But if you rearrange them and do some factoring, you come up with this. So our first digit in our answer is a. And remember that what we start with is just the square root rod, which has the squares in the first column. So there's your a squared. But then we double the a. Whatever our first result was, we double it. And then we look and try to find our next digit. And you can just see how this keeps going. Then you've got the double of a plus b, the double of a plus b plus c. So these are the rods you keep putting in, 2 times each result. And then you get d times d, which gives you the d squared. And that's why our square root rod keeps hanging out in the back.